Hello, hello. All right. Okay. Hello, Noreen. Hi, Noreen. Good afternoon, Yulia. Hello, Al Medina. Good, thank you. How are you? Hello, Elena. Hi, Rachel. Hello, Diana. Long time. Hello, Grisella. Hi, Kareem. Hello, Cassandra. I think it's long time no see. Oh, no, it's not long time no see, but yes, long time no see. Hello, Cassandra. Hello, hi, Kareem. Hello, Grisella. Hello, Diana. Hi, Rachel. Hello, Elena. Hello, Noreen. Thank you. Good, thank you. How are you? But I'm not asking, but I am. Hello, Al Medina. Good afternoon, Yulia. Hi, Noreen. Okay. All right. So first of all, yes, we do have another short class today. I still have this fantasy that I'm going to make a kind of a not enormous, but sort of big-ish video and ask you to watch it and give you points for it when you do your practice exam. Like I'll make a video I think that is really what I'm going to do is make a video that will be part of your practice exam that will help you for the final exam, that will maybe like a review video or something. And it'll be longer than 75. Oh, okay. I'll check that in 1 second. And it will be longer than 75 minutes and be an attempt to sort of make up for some of this class time that we have missed, unfortunately. And I have missed you, but I will say, and I'm going to look in the chat. Good evening. Oh, good evening. I see there is something in the chat, but good evening, Adriana. But let me tell you all, what I'm trying to say right now is I think I owe you some class time, and I'm hoping to pay that back. But I'm very impressed and very happy that any of you could be here on Wednesday night before Thanksgiving. I mean, this has always been a thing at John Jay. It's always driven me crazy. Whether you're physically on campus or just making the time on a computer, I mean, whatever it is, you're making the time. And I know that it's tricky for me, so it's got to be very tricky for you. And it speaks a lot that you would be here at this time. And also, and it's also confusing because you probably didn't know whether to come here at 3:05 or 4:30. So the fact that you are here now under confusing conditions, you are to be commended. And if it's not already clear, you get 14 points just for that. If you saw, I know a lot of you did, but if you saw that little notification or whatever, that was just confirming that we had class today. And if you just fill that out, you just write one word yes, you get 14 points for that, just for the fact that you're staying in tune and haven't lost the faith or dropped off the bus or mixed the metaphor or whatever. So I appreciate it. So that's what I'm trying to say with all that. Like, you deserve commendation for the fact that you're still in it to win it with this class or with any class. Now, but there was something in the chat maybe about that. Hold on, let me just look. I saw something in the chat. Yeah. Oh, sorry. Oh, God. Thank you, Marlon. Oh, you get points for that. I did. I know exactly what you're saying. I'm sorry. That is literally, let me get rid of that right now. Actually, I'm sorry. You're absolutely right, Marlon. Whoa. And there it just went. I was trying to put out class notes from the last class and it kept failing. So I did a test and it kept going to this class. It meant test in the sense of like test of the message disseminating system. It didn't mean exam or anything like that. And I didn't mean for it to go to you. Let me erase it right now so there isn't confusion, but thank you. Yes, you're right. That did just happen. Hold on. Let me just delete that right now before it confuses someone else. But thank you. But yeah, totally a glitch. But definitely did happen. Hang on one sec. Oh, yes, test. Right. Good catch. Thank you. Hang on. Yes, I see. Okay. Gotta love Google Classroom, really. Jesus. I mean, I do anyway, but okay. Thank you. Sorry about that. Thank you, Marlon. Seriously, you should get points for that. And you can. I mean, I'm sure there's a portal that you can put in. Okay. Now, again, it's a short class. I'm not going to pretend to get it. I promised you, when we get back from this little break from Thanksgiving, we'll start dealing with your strange final exam that we'll have a practice. We'll have an optional part for points. And I think the more I think about it, that's what I'm going to do. I think we're going to make part of the points that you will get would be to watch a video that I make that will make up for some of this time and everything. And it won't be hard. It'll be for the sake of review. But that'll just hopefully make us both sleep better at night. So in the short term, there's a couple of things that I really do want to accomplish today with you guys, but I want to ask a couple of questions. Hang on. Yeah. Part of what I want to do, we'll go back to what we were racing to finish last time, which was these notes. I mean, they're up. So I want to, so I have a couple of questions to ask you. My first question though is, what did you do yesterday with Walters? What motion? Yeah, okay, cool. Okay, great. That's right. Okay, thank you. So, okay, if that's the case, Ohm's law. All right, no, that's very helpful. And you all get points for answering that. Like, seriously, thank you for closing the comment. Right, Ohm's law on light bulbs, great. So circuits. And is this fair to say? That was that the first exposure to electricity that you've had with Walters, or did you also talk? No, last week you also talked about electricity. Is that what you're saying, Kazi? Right. Oh, great. Oh, great. Great. That's what I was. Okay. That's very helpful. And that's cool. It means you know something. Okay. So you know what then? That being the case, and given that time is of the essence, I have some loose ends that I want to tie. I'll just admit that there are some loose ends and some things that I still want to nail down from what we did last week, but we did technically get to the end. So even if I have loose ends, I think it's best, since now that you're this deep into electricity with Walters, I want to let's get into that. Let's bring the two pieces of this course together. So so bear with me for a minute as I switch the notes. Hold on. Let me start with, so what I'm going to try to do is say a bunch of stuff in the hour 50 minutes. I want to say some things about electrostatics, about electricity. I'm going to try to say things that are different from Walters, but bring it into the same place as where you are with Walters. So ultimately, our two perspectives should converge. The very first equation on the page, is that familiar to you?
Yes,
okay.
Except for the K
and
the
okay.
S.
All right. Well, let me ask on it. Well, and then fair. This is a real question. This is not a statement. So the first equation is not familiar to you. Is any of the equations on that page familiar to you?
The second one is without the
And
K.
be honest, like this is not a quiz. I really want to know. No. Okay. Okay. Um. Oh no, I can't hear you. Oh. Oh my God. No. And I had a feeling you were talking. Sorry. Okay. I can't. And you know what? Oh my God. My whole last class, I couldn't hear you and I didn't realize it. Okay. Wait. So, right. No, it's totally my bad. My speakers were off and I didn't even realize it. I'm sorry. Go. Talk again, Kazi. I'm sorry. I can hear you now, I think, if you talk.
Hello?
Yes. Okay. Because I saw
Yeah,
you.
yeah, okay.
Okay, sorry. Okay, go.
Oh, I was gonna say that only the second question is it's the second equation is familiar to me, but we didn't like cover what the K is.
Wait. Oh, okay. The second equation is familiar to you, and you didn't what? What did you say after that?
We didn't cover the K because KQ. I don't know what K is.
Oh, okay. Okay. Great. Okay. So something like this familiar. Something like this. Is that or tell or
Yes.
okay. Okay. Great. Okay. Great. Okay. Okay. So let's do it like this. And that was motion number 8, presumably. Well, it doesn't matter actually what motion is. Okay. Yes. Okay. Great. Thank you. And you can talk now. The speaker's on. I'm sorry. I can't believe I just went through a whole class and didn't even realize that. Okay. Okay. So is this statement that I just wrote down, is this consistent with the way you guys, and tell me honestly again, because we are trying to, I mean, it's that point of the year. No one's trying to fool anybody here. Okay, great. I like the way, exactly that. All right, sweet. You get tons of points. Okay, cool. So this is our understanding as of now. Cool. Okay. Then I'm going to add some details. Basically, I'm going to just keep adding layers of details to this, and you stop me or you tell me if the detail is familiar or if I've pushed the detail into a new territory. Okay, I'm just going to just keep layering this. But this part so far, you established in motion 8, like 2 weeks ago, whatever in the lab, like you're comfortable, or just stop me when you're on, whatever. Just keep providing the good feedback that you are. So we have this, right? So now I'm going to say, Cool. This is awesome. You totally really can use the microphone. Maybe I'm scared of hearing what you're so stuff. So that's not familiar. But that's, or were you just, I don't even know if you're joking or not. Now I'm laughing either way, but you didn't. Okay. So I'll say this. All right. So so good. So now I'm going to teach you. So, okay. And this is good. And I'm really appreciating what Kazi's doing right here. And I'm going to just want to make sure that she's not the only one. Like, I don't only want to talk. I mean, I don't mind, but like, so what I'm understanding from Kazi here is that you guys have this concept that you're somewhat comfortable with, like you established at least one time you did a simulation or a lab or whatever to establish that, like if you have some amount of charge sitting somewhere, and by charge, we mean that property that seems to be created by or contained in protons and electrons. Like, I don't exactly know what it is, but this property of nature that seems to come in two varieties, positive and negative. If you have a certain amount of charge sitting somewhere, it will create a field. We'll get into what field is in a minute, but it creates a field. The more the charge you have, the stronger the field it creates, and the farther away you are. So it creates a field, whatever that is. And I'm not assuming that everybody's totally comfortable with what a field is, but just the word for the moment, we're so far saying that if you have some amount of charge somewhere, some electron sitting somewhere, or some proton, or maybe some bunch of protons all squeezed together in a really tiny space sitting somewhere, we're saying so far that those protons will create a field everywhere around them, will create something that seems to have a numerical magnitude, and in fact, even has a direction. And the magnitude of this field, and again, let's even just, I don't even know what field means exactly yet, but whatever it is, we're saying that an amount of charge creates a field, sorry, someone's here, creates a field everywhere at all the points that you can imagine around. And at any point you choose, the strength of the field is directly proportional to the amount of the charge sitting there. And it's inversely proportional to the square of how far away you are from the charge sitting there. Like, the farther you are, the weaker the field. And the smaller the charge, the weaker the field. And we still don't quite know what a field is, but so far, that's what we're saying about field, right? And again, stop me if that doesn't make sense. Well, I want to start telling you what a field is, but the way I'm going to start telling you is I'm going to look at, no problem. All good. No problem. I'm going to tell you, try to break down what a field is, what this number is that we're calculating. But in order to do that, a field is some kind of measurement. Like, what we really are saying is, if you put a bunch of protons down here and you measured the field nearby, you'd get a number that will be bigger, depending on how big this charge is here. And it'll be smaller, depending on how far, if you're farther away. And I think we'll start to get a sense of what that thing is that you're measuring if we look at the units going on. So first thing I'm going to say is charge. Charge is measured in units called coulombs. And I'm not assuming you knew that before. I'm telling you that. And I'm going to break it down even further. But just for perspective, I'm talking about units of measurement, like SI, like NKS units. So just for perspective, I mean, in the same way that I mean, they are called meters, but so just like, I'm saying, so you got this charge sitting somewhere. You get a certain distance away measured in meters. You're going to square that. You're going to plug that into the denominator of something, and then you're going to measure how strong your charge is. Now, I'm telling you, and again, I'm going to ask you to stop me in a second if okay. Charge is not measured in meters, and it's not measured in kilograms. It's measured in something called coulomb. Now, that's just a unit of measurement. I'm just sort of like telling you, but let me give you perspective on like how big or how small that unit is. So I'm going to turn the page. Stop me if that's not okay. To give you perspective on what coulombs are, let me remind you that the best thing I know about charge is that it's something that seems to be contained in or characteristic of or generated by protons and electrons. Like they are our fundamental little building blocks or packages or carriers of charge. So if I want to understand charge, I'm going to understand it through protons. No problem. Okay, totally understand. No problem. Got you. So is mine. So to give you perspective on coulombs, I'm going to relate it through protons and electrons. Okay. So just for perspective now, and for mathematics, like when we measure charge, when we say charge creates field, and again, I still haven't really exactly said what field is, but it's something. When we say that charge creates field, more particularly when we say a point charge, a point source of charge creates field, we're picturing protons and electrons. Like ultimately, that's how we make charge, is with protons and electrons. But we measure charge in coulombs, and 1 coulomb of charge is actually an enormous amount of charge, i.e., it's an enormous number of protons or electrons, i.e., or put another way, the charge of 1 proton turns out to be the exact same in magnitude as the charge of 1 electron, just opposite in direction. The charge of 1 proton is the same as the charge of 1 electron, and that charge is approximately 1.60 times 10 to the negative 19 coulombs. Negative 19, now that's a tiny, tiny number. 10 to the, and when I say approximately, please remember, this always happens in science. When I say approximately, I'm not saying because I don't really remember, or I'm not saying like it's a guess. I'm just saying that the actual number is a series of digits after the decimal point that continue on forever with no repeat. So we're chopping digits off. Like we're saying that this is a measured quantity and it's a natural quantity. So there's no reason at all that this quantity would have ended up being something like exactly 16 or something. Like it's just a very, it's a transcendental number like pi or e or Planck's constant or anything else. So we chop off the digits after 2 significant digits. And so that's why it's approximate. It's not like a lie or something. but it's approximately 1.60 times 10 to the negative 19 coulombs, 0.00016 coulombs. So that's a very tiny amount of coulombs. It might seem like it'd be more convenient if the fundamental building block of charge is a proton or an electron. It might seem more convenient to call the unit of charge in a proton like 1 coulomb or something, and maybe it would be more convenient, but that's not the way it is, basically because it takes a lot more than 1 proton or 1 electron for us to start detecting charge and start playing with charge and start measuring charge. In fact, the way that we measure charge and play with charge historically is first through electrical currents in wires, as you're doing with Walters now, and I'm going to get to that next. But the truth of the matter is it's a lot easier to do labs and play with and understand charge once you get a whole bunch of charges moving through wires. So a lot of what we understand about electricity, we've retro-engineered and historically we figure out what we can see, and then we infer from that what we're seeing is built on. Okay, and I'm going to look in the chat in 1 second, but boy, my Wi-Fi is pretty weird too. Oh, sorry. Am I going in and out? Wait. Okay, hold on. I am looking at chat because I have a feeling I'm going. 1 second. I'm going in and out. Okay. Wait. Oh yeah. Sorry. Hold on. Okay. I'm looking. I'm. Okay. So Kazi saw that it was a large number. I'm looking at the chat. I see that I'm going. Yeah. Okay. I'm seeing it too on my end. That's the good. So is it not happening right now? Is it good right now? It's gonna. Okay. So the one thing is, well, I'll try to do one thing to. Okay. If it happens again, I think there's something I can do, and I think I now realize. If it happens again, I think I'll know it, and I'll do something about it. Sorry. Okay. Plus it takes me this long to find my voice anyway. So I'm just saying the amount of charge in an electron is very tiny. And it might seem inconvenient that the units that we use are so cumbersome like this, but it's because it takes a lot of protons and electrons for us to be even able to play with charge and discover things and make measurements in the first place. In fact, it's a lot easier to get a whole bunch of charges and start putting them in motion through wires, i.e. electricity, i.e. Ohm's law, i.e. electrical current. That is a much easier way for us to study and measure and talk about electricity. And it was a much easier way historically too. A lot of what so if it feels like we're going a little bit backwards in the course or something, like if all of a sudden you jumped in and we're doing wires with Walters, before I'm even saying anything about electrons, in a way, that's the way the history went as well. It's easier to understand and play with electrons after you gather a whole bunch of them and you start sending them through wires. Oh, I'm going in and out again, aren't I? Okay. Okay, good. And I'm seeing, okay, thank you. And yeah. Oh, great. Oh, great question. Okay. So let me say, first of all, Kazi's question about, is there a way to relate like volts and coulombs? Ultimately, yes. And ultimately, that's like where I want to go with all this. I'm not even, that's a good enough, that's a super fair question, a super important question. The answer is just complicated enough that I might not even get to it by the end of today, although that is sort of my goal, is to relate all these things by the end of today. So totally right on. And that was sort of the goal in history, was to see, again, it's easier to relate to what's happening in the wires than it is to what's happening down deep in the atoms. But my goal is to relate those two to you today. So yes, and then what's the last word down the bottom? Oh, tiny volume. So down at the bottom of the page, it says tiny volume. So, okay, cool. So what I'm trying to say here on this page, and then I'll change the pages, I'm just saying that from here on in, if anybody ever talks about a point charge of 1 coulomb of charge, or even better, if they talk about -1 coulomb of charge, because they're thinking about electrons, because electrons generate electricity. Okay, if someone is ever talking about a point source of -1 coulombs of charge, they're talking about an enormous amount of charge, as it turns out. They're talking about like 16 quintillion electrons all jammed together in a tiny, tiny space. Now, the fact is electrons are tiny, so you totally can and do have this all the time. Like we can have 16 quintillion electrons in a tiny, tiny space and then start sending them through wires and cause electrical currents, which is what I want to talk about. But just for starter perspective, electrons are that small in charge. Why is it called electricity? Why are we so concerned about electrons? Because electrons, as you know from chemistry, live in the orbitals, the outsides of atoms, and can be dislocated from atoms. Atoms can be ionized, so electrons can become free and move through metal objects on their own in a way that protons really can't. Protons are locked in the nuclei of atoms. So what we play with when we want to play with charge tends to be electrons, and we call it electricity. Unfortunately, historically, we call the proton a positive thing. We call the electron negative thing. So we have a little bit of an annoyance with that we're having all these negatives move around all the time. But if negatives move to the left, it's equivalent to positive charges moving to the right. So it ends up not really being that big of a problem. But what we're focused on, what you're focused on in the lab, is electrons, coulombs, moving through circuits. In fact, at the risk of incoherence, let me try to answer Kazi's question right now. In fact, sorry. Oh, cool. Okay, I'm glad. So as long as, so it's Kazi Day, national holiday. The day before Thanksgiving is Kazi. Great. So I'm going to go with this Kazi momentum here for everybody. Forgive me, and everybody else. Obviously, I totally see that Shasha's here. I see that everybody's here. I'm just sort of teasing around, but her questions are very relevant. So I'm going to stick with this Kazi thing for a minute, and I'm actually going to try to answer in part her question. Like, how do these coulombs? So before I go back to fields, let me just jump right now and relate this a little bit to the electrical currents and the Ohm's law and everything you're looking at in the wires. Whoa. Okay. Unit wise, and you're looking at current and voltage and resistance in the lab right now. I know Kazi just asked about voltage, about V. That's going to require a little bit more of an answer on my part, but just to start backing my way into an answer here, let me say that you may or may not recognize A is the unit for current, right? I mean, in lab, presumably, I don't want to get all, in lab, presumably you said something like motion 9. Is it fair to say motion 9 was like V equals IR or I equals V over R or something like that? Was yes. Okay. So the great. Okay. So the I, the capital I in that statement, current, electrical current, and I'm going to say this on the next page in a deeper way, but electrical current is measured in amperes, amps, and an ampere is a coulomb per second. I'm going to be more specific about that in a moment, but to start answering anybody's question, how this all relates together, what electrical current is, if I put an ammeter somewhere in a wire and I'm asking like, what's the electrical current? And if the ammeter is, if I put an ammeter somewhere in a wire of a circuit, and the ammeter tells me, oh, there's 100 milliamperes of current going through the ammeter right here at this point in the circuit. What it's saying is, if it says 100 milliamperes of current, what it's saying is there's 100 millicoulombs of charge, of electrical charge, passing that location, that fixed space point every second. An ampere of current is literally a coulomb of charge per second. I'm going to say that, in fact, hopefully that puts some perspective on this. And I'm going to say it I'm going to now say it in a calculus way for those of you who like calculus. And again, this is not required. If you don't follow it, you can ignore this if you don't like calculus or whatever, but it might actually put perspective for some of you. What current technically is dq dx times dx dt. dq dx is like infinitesimal amount of charge per infinitesimal length. It's like ratio of charge per length. It's like one-dimensional charge density. That's another way of putting it if you like. Right? Like all derivatives are infinitesimal ratios. They are rates of change where rate means ratio, right? A little bit of rise per a little bit of run. So if you have a little bit of charge per a little bit of length, charge per length, it's like amount of stuff per space. It's a density. It's like how much charge do you have per? So like in other words, one last way to put it here. One last way to put it. So if we're thinking, so what current is a little bit of charge per a little bit of length, as in like coulombs per meter, like ratio of how many coulombs of charge you have per each little meter of some wire. That multiplied by dx dt. What's dx dt? Infinitesimal rise in position, like infinitesimal displacement per infinitesimal time, like or infinitesimal length per time. In other words, what current is little lines of charge, each moving with some velocity, little lines of charge moving with velocity, little coulombs per meter moving at meters per second. Well, the meters cancel out in the units, right? Or in other words, the dx, even though you're not always allowed to do this in calculus, but sometimes you are, the dx's cancel out. And what you end up having, what the true definition of current is again, this is really cool if you like calculus. It's not as cool if you don't, perhaps, but what I'm saying is what electrical current is flow of charge. What we mean by flow literally is what the measurement of, if we had a bunch of lines of charge, each one of which was moving at some velocity. If you think about it, whether you think about it in calculus terms or just unit analysis terms, we're talking about charge per length times length per time. The lengths cancel out, and what you end up having is charge per time. In other words, what I'm really saying is current is it moving charges. Current is moving charges. When you measure current in a wire, you're measuring the motion of charges through that wire. But let's be careful. And what's cool about it is, in a way, is you're not when you measure current and you say it's 100 milliamperes, right? This is actually a real measurement. It's not. It's a type of measurement of motion. It's not the same thing as speed or velocity, for that matter. You're not, when you say the current is 100 milliamperes, you're not saying, oh, any individual charge is going 100 miles an hour. Like, it's not speed. You're not rating the distance per time that any one particle undergoes. What you're doing is you're counting charges as they fly past a given fixed point in space. So it's charge per length times length per time. The length cancels out, and what you're counting is charges per time. You're counting how rapidly or how voluminously charge flows past a given point. So it would be like standing on the highway. Measuring current is to charge as what traffic would be like if you stood on the highway and you were measuring traffic, and you didn't just take a speedometer and measure how fast any individual car was going, but you just stood on the highway and waited an hour, counted the number of cars that went past you in that hour, and then divided by 60 minutes or, and divided by 3,600 or whatever to find out how many cars on average were passing every second. That's what we're doing. We're counting the flow of charge per time at a given point in space. So charge is current literally is coulombs per second. dq dt is what current is. That still doesn't answer Kazi's question about voltage, but that's what current is as related to charge. Let me just see the chat. I think things happen in the chat. Sorry. Oh, no problem. Oh, great. Oh, thank you. Okay, cool. Okay, so hopefully this is clear so far. Now, so strictly speaking, for those of us in calculus land, current is like the simple derivative, the simple time derivative of charge. That's really what it is. It's the derivative of charge. So if you understand charge is measured in coulombs, you understand current. But what about voltage? Voltage is a little bit more complicated. Well, for voltage, that brings me back to the concept of field that I was sort of starting to say at the beginning of all of this. We said field is generated by charges at certain distances, right? Okay, so just to read this so it says back to E fields, back to E field. What do we mean by field? Very fair question. Well, I'm going to try to answer that question in the same context as we're talking about these other things. I'm of the opinion right now, or of the perspective, that as scientists, we can get our best feel of these different quantities by thinking about the units that they're measured in. The units tell us a lot, especially if they relate to units that we already know something about. So I'm going to try to answer what a field is by telling you what units it's measured in. If you have a certain point source, if you have a certain source of charge, like a bunch of protons sitting here, a bunch of electrons sitting here, and you measure the field over there created by those charges, what you're measuring something in field, electrostatic field is measured in newtons per coulomb, like N over C. That may sound a little abstract or a little surprising, or maybe it doesn't, I don't know. I will also tell you that gravitational fields are measured in newtons per kilogram. What's going on? Like, what am I getting at? What a field is a force waiting to happen. Let me tell you what I mean. Okay, first I'll just read what this says here. This says a field is a force per object, like a force per object, like force. You might recall from physics 101 or whatever. Force is measured in newtons. Fields are always measured in newtons per something. Like gravitational force is measured in newtons, and gravitational force is something that one mass does to another mass. Gravitational field is measured in newtons per kilograms. Electrostatic force is something that one charge does to another charge. Electrostatic field is measured in charge units. Sorry. Electrostatic force is something that one charge does to another charge. It is measured in newtons. Electrostatic field is something one charge does to space. It is measured in newtons per coulomb. Let me be more mathematical and really show you what, but you'll see the equations that I wrote on the very first page at first and asked you if you'd seen before, you'll see them now. So I'm just going to write 4 equations now so you can see a parallel or see a pattern. You may recognize some, you may not, but you'll see a pattern when I write them down. Okay. In a way, this is a lot of information. In a way, it's not. Let me see if I can break this down. And some of this might be familiar from physics 1, maybe it's not. But it is the case that given any two masses in the world, any two masses in the universe, any 2 points of mass, like sun and earth, well, yeah, I mean, strictly speaking, any 2 points of mass. So like a point at the center of the sun and a point at the center of the earth, let's say, or so a bunch of kilograms of mass crammed into a tiny space. We did. We did. Wait a minute. Oh, cool. Great. Thank you. That saves me a lot of time. Okay. Great. Okay. Thank you. I appreciate the honesty too. And that will make me less frantic. Okay. Kazi. Okay. Okay. So if you've already sort of seen that, yes, a big similarity between gravity and electrostatics is that they're both, well, mathematically, they're both inverse R squared phenomena, right? They're both inverse R squared phenomena mathematically. Physically, they're related in that they're both action at a distance phenomena, right? The similarity, the reason that whenever anybody's trying to teach electrostatics or understand electrostatics, they always bring it back to gravitation. We all do, all physicists do, because both phenomena, the electrostatic phenomena and the gravitational phenomena, have this shared property of seeming to act through empty space. They both involve pulls and pushes that don't seem to require any physical contact. Like literally, that is the fundamental. In fact, that's why they're called fundamental forces or fundamental interactions. The sun doesn't have to do anything, evidently, in order to be pulling on the earth. It just sits there, and its mass automatically, apparently, reaches out through empty space and starts yanking on Earth. Similarly, the Earth just sits there and reaches out and yanks on the sun through empty space. Like they don't seem to be having to touch to do that. And if you put anything in between them, that doesn't stop them from touching. It doesn't stop them from pulling. Gravitation is a pull, is a force that seems to act between masses through empty space without any physical contact, without any activity or like planning or event, right? Same thing with electrostatics. Protons seem to be able to pull on electrons, and protons seem to be able to push on protons simply by existing in space. They do this. So both the gravitational phenomenon, let's say, and the electrostatic phenomenon are known as fundamental for this reason, that they just occur in space, and they occur between any and all. Like gravitation is exerted by every single mass on any and every other mass in the universe, and electrostatics is exerted by every single charge on every other charge through space. So they're called fundamental for this reason. And then also strangely, they end up having this exactly the same mathematical form. Pardon me for 1 second, excuse me. Okay, sorry. Okay, now here, but presumably everything I just said in a way you already saw from Walters. I mean, it is a very big deal in physics that all interactions that have this shared property of action at a distance also have this shared property of mathematics. Oh, sorry. Yeah, no, this is a big. That's great, Alex. Yeah, I mean, and really, this is one of those things. Like, if I'm not careful, I could. Walters and I, if I'm not careful, like we could really go down the rabbit hole with this, because like this stuff, this action at a distance business is what kept Newton up at night big time, and then led paved the way for Einstein and all that. Like, this is a head scratcher for physics. Is like, how is it that objects pull on other objects through empty space without touching? And then how, well, and some of this has been resolved. I don't want to say that it's all mysterious at this point, but for a while it was also mysterious. Why is it that every time we have a force that seems to have that quality to it, or why is it every time we have a phenomenon that has that quality to it, it is described by mathematics that have a r squared in the denominator? Like, what? Now, that turns out to be very explicable, believe it or not. Like, it actually totally makes sense in the end, but it doesn't look like it makes sense right at first blush. But here's why I'm getting into it now with you. What I want to try to emphasize is the discussion begins with forces. Like, first we understand forces in physics 1 or in the earlier history of physics. What we understand, and a force is always, whether it's a fundamental force or not, whether it's gravity or it's friction or tension or normal or whatever, a force is an interaction between two objects, like always. And in fact, I want to leave this page up for the moment, but you might want to write that somewhere. A force is an interaction between two objects. And that means between two thingy things, two discrete, identifiable, countable, material, massive objects. One object will exert a force on another, meaning one object pulls or pushes on another. Now, and it's easy to see that a lot of times, like, I pull on a fish with a fishing line and the fish pulls back on the fishing line. That's one example. Or I push against a wall and the wall pushes me back, et cetera, et cetera. And then we all accelerate and blah, blah, blah. Now, some forces seem to be able to do this pushing or pulling through empty space. Gravity is one, electrostatics is one. But let me remind you, or let me explicate to you with these equations. It begins as a force. That is, that for any two masses in the universe, this is what I was saying before, any 2 point masses in the universe, one point mass will exert a gravitational pull on the other point mass, like whether it's a point in the center of the sun and a point in the center of the earth, or a point in the center of the earth and a point in the center of the moon, or a point in the center of the earth and a point like in my pen that the earth pulls down. Whatever it is, one mass pulls on the other with a force that is directly proportional to the mass of each of the objects. So the bigger either or both of them, the bigger the magnitude of force, and smaller in a manner that's proportional to the square of the distance between the two of them. So what the top equation says, what I'm trying to be clear about is, first and foremost, what we understand, what we observe, what we measure, what we see and believe in the world is the gravitational force that one object exerts on another. And that force is measured in newtons, like all forces are. And that force creates masses times creates accelerations like all forces do. So unit wise, if you want to know the gravitational force that the sun is exerting on the earth, what you do is you take the mass of the sun, you multiply it by the mass of the earth, you take the distance between them and you square it, divide one product by the other, and now you have a quantity, and you're just about there, and you just about know then the gravitational force exerted by the sun on the earth. But then you realize, wait a minute, kilograms times kilograms divided by meters squared. That's, if I'm looking for a force, that doesn't make newtons. Like a newton is a kilogram times a meter per second squared. So what happens is there's a constant of proportionality that you have to multiply the whole package by. That's this capital G thing right here that is now written at the bottom of the page. If you want to know the gravitational force that the sun exerts on the earth, you take the two masses, multiply them together, divide by the square of the distance between the two of them, and then take that whole package and multiply it by this one universal number that always works. That is one number always. You could memorize it because it never changes, but you don't have to memorize it because it never changes. It's called the universal gravitational constant, and it happens to be this teeny tiny number of 6.67 times 10 to the negative 11th newtons times meters squared divided by kilograms squared. It all looks very, so I'm talking about what's written at the bottom of the page here. It all looks very obscure in a way at first, like, oh my God, newtons times meters squared divided by kilograms squared. But it makes total sense. It's not obscure at all. It's literally just saying, look, there's got to be a number there that cancels out the meters squared from the denominator and cancels out the kilograms squared from the numerator, and then puts in newtons, a number that makes sure that this whole thing ends up being measured in newtons. So, and the number that makes that work happens to be a really tiny number. So gravitational forces between objects in the universe happen to be, on all other things being considered, very, very tiny. So that big G is just a constant of proportionality that ensures that that the force exerted by one object on another is measured in newtons. Now skip down for a moment, skip down to the third line, the third equation on that page, Fe, the one that I wrote initially and you said you didn't recognize. What that thing there is an expression for the electrostatic force. That's sometimes in chemistry known as Coulomb's law. I mean, it is Coulomb's law, or it's sometimes known as the Coulomb interaction or the Coulomb force. It is the force that any one charge exerts on any other charge. It operates just like gravity. You want to know the electrostatic pull that a proton exerts on an electron? Well, you take the charge of the proton, 1.60 times 10 to the negative 19 coulombs, multiply by the charge of the electron, multiply them together, divide by the distance squared. But then in order to make the units work out to be newtons, the whole thing gets bundled together and multiplied by a proportionality constant, the K thing that you didn't recognize, because that's all it is a proportionality constant. It changes your proportionality motion into an exact equality. I'm not saying you have to memorize this thing. I just want you to see the pattern that K, which happens to be a really, really large number, K functions for electrostatics just like G functions for gravitation. K is approximately 8.99 times 10 to the 9th newtons times meters squared divided by coulombs squared. Same deal. Like, it's just a number that makes the meters cancel out and the coulombs of charge cancel out. So we're left over with a force measured in newtons. You follow? And I know we have 8 minutes left. Hopefully this is making some sense. But what I'm saying is these are forces. Like the first line and the third line on this page are the forces that just seem to exist between masses and between charges. The thing is, these forces, well, we can make predictions based on, we can collect data to support them. We can collect data, and we can make predictions and do things with these force expressions, equation number 1 and equation number 3. But they're very mystifying and very disturbing in a way that they embrace a belief that pulls and pushes can happen through empty space. Like, when you really start thinking about it, it's bizarre that we believe that the sun can pull on the earth through empty space, like without touching it. Or it's bizarre that a proton can pull on an electron without touching it. Why is that bizarre, you might say? Here's why it's bizarre. I mean, maybe it's not that bizarre. Maybe it's just like, well, I mean, look, it's clearly true. I mean, or apparently it's true. Like, things fall. Like, the center of the earth seems to be pulling on stuff like without touching it. So it does seem true. So why should I say that it's bizarre? I mean, if it's reality. Well, what's really bizarre is these equations, the first and the third. Because the equations say that pull that the sun exerts on the earth, or that the pull that a proton exerts on an electron, or I should say that the anode of a battery exerts on the cathode of a battery, like the idea that this charge is rushing, that the current is flowing from one terminal of the battery back to the other terminal, because we believe that somehow the extra electrons are sitting on one terminal, pulling or pushing away the electrons so that they flow to the other terminal. Like, that's what we're believing. And that's what voltage is, even if I don't mathematically get to it today. We're believing that electrons are pushing on other electrons and causing them to flow through a wire and create current. But we believe that this push is happening through empty space. Now, why is that bizarre to believe? Because we're believing that the magnitude of the push and the pull is very precisely depending on the positions of the objects doing the pulls and the pushes. Let me break, and again, I know we have 6 minutes. This is just enough time for me to break this down and explain to you what a field is. What I'm saying is forces that act through a distance cause us to scratch our heads in a very big way. If you just think in the simple case of gravity, and everything I'm about to say about gravity totally applies to protons and electrons as well, but I think it's a little bit easier sometimes to picture with masses. If you picture the sun and you picture the earth, and you picture that what this equation is saying is that the sun pulls on the earth with a precise magnitude that depends not only on how big the earth is and how big the sun is, but where the earth is. So if you believe this gravity idea, that means that the sun pulls on the earth, and then all other things being equal, the earth would start accelerating towards the sun, and it does. So sometimes the sun pulls on the earth and the earth starts getting a little closer to the sun. But now, or just like the earth itself pulls on, like my can of Coke, I let go of my can of Coke, the earth starts pulling on the can of Coke starts falling toward the center of the earth. Well, what happens when it's falling? It's getting closer to the center of the earth, right? So one moment later, when the can begins to fall, it's 1 centimeter closer to the earth. That means that the R in the denominator has now changed. According to this equation, that means that now the earth will start pulling on it harder because the denominator is lower. So the whole force, the whole fraction must be greater, right? I mean, that's math. There's no disputing that math. But then that means that when the thing is even closer, it gets pulled harder now. So now it's going to get closer and it's going to get pulled harder again. Why is that a problem? Because that means that every time this thing moves, somehow the earth adjusts the strength of its pull to account for the new position of the object, but the object is somewhere else in space, not even touching the earth. So somehow we're believing that the information of this object's new whereabouts is getting continuously sent to the earth and getting updating the earth, right? Like literally, if the sun is pulling the earth in a manner that depends on how far away the earth is, that means that as the earth is getting closer and closer to the sun is getting updated with this information and adjusting its pull accordingly, right? That means the information of the earth's location is continuously getting fed somehow through empty space to the sun. And not because the sun and the earth are special, but apparently this is happening with all objects at all times. Anytime we believe in an action at a distance force, we are somehow believing that information, numerical information, is propagating through empty space from one object to another. And when I say the information, I really mean it. I don't mean that the sun is consciously thinking about it. I don't mean that the sun is like, is aware of it. And I don't mean that literal numerals are flying through space. I don't mean it's like Sesame Street. I don't mean that like little plastic, like carvings of like 2 or something are like flying. But I mean the actual value, the position, the raw information of where the earth is somehow must be getting to the sun. And every time the information changes, the change in the information must be somehow traveling through empty space to the sun. And it raises, among other things, and I know I have 2 minutes, but this raises, among other things, I mean, if that isn't already, like, that is disturbing. You could tell, I mean, I know this, but I can never explain this or talk about this without getting myself all hot and bothered, because it's a very weird thing. It's really weird when you really just ask yourself the question, does that freaking take time or not? Like, this is the question that kept Newton up at night. Like, if we really believe, because I'm not BSing you, like, apparently we really believe this, that the sun gets the information of the Earth's, or any proton anywhere, gets the information of where electrons are at any given moment. And every time an electron changes its position, the proton like knows this. So the question is, when the electron changes its information, changes its position, does that new updated information, does it take time to like literally travel to the proton? And I know we have 1 minute, but like when I say the information goes from the electron to the proton, like how literally do I mean it? Do I mean that it actually travels at a finite speed through space to the proton? In which case, does that mean there's a delay every time? Does that mean that all motions are actually going like that? What looks like the smooth movie of life is actually a stroboscopic like stop action thing, because every time we move, in order for the new pull to happen, first the information of our new move has to get there. That's bizarre if that's true. On the other hand, if that's not true, if the information just gets there immediately, does that mean that all information is all places at all times? Like I move and immediately everything in the universe knows that I've just moved, in which case, does that mean it always knows where I always am? And what? Like either possibility is bizarre. Why am I screaming and yelling about this, especially if it's the night before Thanksgiving, you only have 1 minute? I can't answer all the questions right now, clearly, but I can tell you this. The simple one-word answer to all these concerns is field. Now, that's not going to put you to bed at night, but what I'm saying is the second question, the second equation and the fourth, and we're going to go right now. I mean, I know it's 5:40, but just so you understand, in a part to at least allow us to work with such weirdness and make predictions in physics. I'm not saying I can answer all of that right now. Like Newton couldn't. He went crazy. Like he died crazy over this. But one thing we can say is, or one thing we do say to at least make our life manageable, is we say, okay, fine. Like that can't, no, like you can't send this information just through empty space with that. There's got to be like a medium. There's got to be some kind of conveyance of this. The information has to somehow propagate from one object to another in some sort of medium, kind of like wave pulses. So we say, and this is the last thing I'm going to say, and thank you for being so patient, but this is the last thing. What we say is, you know what? It's not that the sun exerts a force directly on the earth. That's too much for us to swallow. What we say is the sun creates a gravitational field everywhere in space around it. It is the body, the medium that contains the information of the sun's mass and where it is. Everywhere around it, it places a little vector, so to speak, that contains the amount of newtons of force that would be exerted by the sun towards the sun on every 1 kilogram of mass that could ever be placed at that location. And then if we place masses at any location, then, so we say, we don't say sun exerts force on earth. There's a lot, I promise. I thank you for your patience. We don't say the sun exerts a gravitational force on the earth anymore. We look at the second equation. We say the sun exerts a field, and then the field exerts a force on earth. One object exerts a force on a second object, but objects that do fundamental things exert fields at points in space, and then the field forces on second objects. Force is something that one object does to another. Field is what one object creates in space. So the field is all the information of the first object divided by the information of the second object. A field is how many newtons of force would be exerted per every coulomb of charge that would be placed at that location. I'll just end it. Okay, so field is force per object. Field is newtons per coulomb, or in the case of gravity, newtons per kilogram. That's it. Sorry, I know I went a little bit over there. I'll hang out for a second in case there are questions, but have a great Thanksgiving otherwise, and then we'll talk about the final everything when we get back. Have a great, you've been very patient. Have a great Thanksgiving. Thank you. Thank you. And I'll turn it off. Thank you. Have a great vacation. I mean, a great Thanksgiving.